We've invented a device that can take water from humid air and sunlight and convert it into hydrogen, which can be used as a fuel or a chemical feedstock for a future energy system based fully on renewable energy. Our technology has been enabled by this, a transparent, porous, conductive substrate, which for the first time allows a semiconductor to be coated and have a large surface area to interact with the humid air. This is really important because there's really a lot of sunlight available, but the sun doesn't shine all of the time. So we need a way to store the sunlight for future use. And using sunlight to split water into hydrogen and oxygen, storing the sunlight in the form of hydrogen, is a leading method to do this. Our work was inspired by the way a leaf works. Natural photosynthesis occurs by taking carbon dioxide from the air together with sunlight and produces sugar, effectively storing the sun's light in a chemical form.
So in our lab we have a lot of experience with a semiconductor, but usually we coat them onto a flat surface. Here we have a three-dimensional network, so that was a challenge to find the appropriate method to coat this semiconductor material on this new template. So to develop our photocathode electrode for hydrogen production, first of all we took some quartz fibers that we blended in order to homogenize the fiber length.
We filter them and compress them into a wafer.
We make a quartz fiber template by heating the fibers at 1350 degrees to melt the fibers and connect them together in a network. And then the second step is to make this transparent porous support conductive by coating a conductive layer, which is also transparent on the top.
Now the challenges here are to find a system that has the right porosity, the right mechanical properties, and sufficient transparency and conductivity to enable this gas phase photoelectrochemical reaction. Coating that with a light-absorbing semiconductor material gives us our final photoelectrode that, together with a catalyst and integrated with a membrane in a photoelectrode membrane cell, can make an overall solar to hydrogen production device in the gas phase. This has been previously shown by our groups and others in the liquid phase using liquid water, but it's not very practical to imagine a liquid-based solar cell on the roofs of our houses. Instead, we can imagine using the humidity from the air in the gas phase and splitting that into hydrogen, but that hasn't yet been possible to date because current technology is using gas diffusion electrodes that are opaque. This one's made from carbon-based material. It absorbs the sunlight and prevents our semiconductor material from absorbing the sunlight and performing the reaction. So our work has been to develop a transparent and porous conductive substrate which can allow us to coat it with the semiconductor material, giving it the ability to absorb the light and convert the water into hydrogen in the gas phase. Our initial demonstration of the proof of concept of this device is only a first stage. The overall solar to hydrogen efficiency is still quite low, but our invention of the transparent, porous, and conductive substrate now opens the door to advance this technology further. So our next step are going to be to optimize the pore size, optimize the thickness, and optimize the mechanical properties, as well as investigating the coating of different semiconductors and different catalysts to improve the solar to hydrogen conversion efficiency of this type of device. In the future, if we're successful to find a system with a high enough solar to hydrogen conversion efficiency and good enough stability, we can imagine these artificial leaf-based systems both in arid environments like the desert where there's not a lot of liquid water, but also in more humid environments like the Lake Geneva region.